Life is full of processes to learn and then relearn when they become more elaborate. One day you log into an app with just a password, then the next day you also need a code texted to you. One day you can just pop your favorite microwavable lunch into the oven for 6 straight minutes. But then the packaging changes and you have to cook it for 3 minutes, stir, and then heat it for 3 more. Our brains need a way to keep up. A new study by neuroscientists at the Picower Institute for Learning and Memory at MIT reveals some of the circuitry that helps a mammalian brain learn to add steps. In Nature Communications, the scientists report that when they changed the rules of a task, requiring rats to adjust from performing just 1 step to performing 2, a pair of regions on the brain's surface, or cortex, collaborated to update that understanding and change the rat's behavior to fit the. I started this project about 7 or 8 years ago when I wanted to study decision-making, said Daigo Takeuchi, a researcher at the University of Tokyo who led the work as a postdoc at the Riken MIT Laboratory for Neural Circuit Genetics at the Picower Institute, directed by senior author and Picower P. New studies were finding a role for M2. I wanted to study what upstream circuits were influencing this. Tripping up the second step, Takeuchi and Tonegawa traced neural circuit connections that led into M2 and found that many originated in the ACC. They began to see the ACC's role in guiding M2's sequential decisions when they instilled a genetic manipulation in ACC cells that allowed them to suppress their activity. Compared to rats with normal ACC activity, they failed for much longer to realize the second poke was necessary. Rats had no trouble, however, going from 2 steps back to just 1, regardless of whether their ACC was silenced. They also silenced other areas of the cortex, but doing that didn't affect the ability of the rats to notice and adjust to the rule switch. But what effect does the ACC have in M2? Takeuchi and his co-authors measured the electrical activity of cells in M2 as the rats played their nose-poking, rule-changing game. They found that many cells were particularly activated by different task rules, i.e., 1 step or 2 steps. When they silenced the ACC, though, that suppressed this rule selectivity. They found that when they silenced the ACC, this actually increased the activity of the negative outcome encoding neurons during negative feedback, particularly for the first 10 to 20 rounds after the rules changed from 1 step to 2. This correlated strongly with the timing, or epoch, of the rat's worst performance. The team further confirmed that the feedback, or outcomes, stage mattered by using a different technique to silence the ACC. By engineering ACC neurons to be suppressed by flashes of light, a technique called optogenetics, they could precisely control when the ACC went offline. These results indicate that ACC neurons process error feedback information following an erroneous second response and use this information to adjust the animal's sequential choice responses in subsequent trials, they wrote. Too high a threshold. The evidence painted a clear picture. When the rats needed to notice that an extra step was now required, the ACC's job was to learn from negative feedback and signal M2 to take the second step. Is there another circuit for noticing when a multi-step process has become a one-step process? If so, is that circuit integrated with the one discussed in this study? And if the threshold model is the right one, how exactly is it working? In addition to Takeuchi and Tonegawa, the study's other authors are Dheeraj Roy, Shruti Muralidhar, Takashi Kawai, Andrea Bari, Chanel Lovett, Heather Sullivan and Ian Wickersham. Nature Communications. 2022. 13. 1. doi. 10. 1038 per second 41467. 022. 32142. 1 Picower Institute at MIT. When a task adds more steps, this circuit helps you notice. Science Daily. https://ift. tt. fm6exos. Accessed August 5, 2022. Thanks for watching. Please subscribe my channel for more videos.